Hello class, my name is Adam Park. The topic that I chose for the midterm topic discussion today was basic properties of the atom. For those of you who have taken Chem 1212 or Chem 1211, this should be fairly similar to this topic. If not, I suggest that you quickly go back and review Dr. Harris's in-depth PowerPoint slides. She posted on the atomic properties within chapter 3.1, I believe. It essentially goes through all of the atom's properties and such. I just wanted to lay over a brief foundation of it and then briefly touch upon some of the complex structures that are formed using atomic properties. Now, if we'll look at the basic structure of atoms, we'll see that, again, they're composed of electrons, neutrons, and protons. Protons and neutrons making up the atomic mass of an atom, the electrons carrying the electrical charge, but carrying a very minute portion of the atom's mass. The protons here, as well as the electrons being involved in the nucleus with the electrons orbiting. I'd like to briefly mention that this is a 2D structure, so that's why these electrons are in perfectly circular orbits. And typically in real life, if you were to do a 3D structure, they're actually going in all these crazy different directions and dumbbell curves and crazy four-leaf clover curves. It's pretty cool. Now, as I mentioned before, atomic number and atomic mass, for those of you who don't necessarily know what those are, atomic number is essentially indicative of the amount of protons and electrons within an atom. The atomic mass, or the atomic weight, is essentially, as I said before, the sum of the amount of atoms with the sum of neutrons. Electrons are not included here just because they are extremely light. Here are just a couple of common elements we use, specifically within the field of geology, such as iron. You got hydrogen, nitrogen, oxygen, as well as silicon and magnesium in there. One of the important topics I wanted to touch on today was isotopes, as it is a foundational aspect of radiometric age dating as well as radioactive decay. Essentially, it just is really measuring the amount of atoms that have degraded into their natural form. An isotope is, in the first place, just an atom that is the exact same as another atom. It's just that the only difference is it has a different number of neutrons. The result of it having a different number of neutrons is that it varies in atomic mass as well. Unstable forms of this result in radioactive isotopes and are hence the whole driving factor behind radioactive age dating. Here is a nice little exponential graph showing the amount of parent atoms slowly being converted into daughter atoms. The half-life is classified as the amount of time it takes for half the parent atoms to be converted over to daughter atoms. A common example of this is carbon. So on a close-up, like single atom view of this, essentially an atom would start off as, say, carbon-14, and then gradually over time it loses neutrons as it declines into carbon-12, and its atomic mass degrades into carbon-12, let's say. Valence electrons, if you guys aren't familiar with this, this just has to do with how the atom binds and who it wants to bond with. valence electrons are essentially specifically focusing on the amount of electrons present within the outer shell of an atom's nucleus. Say, for example, this atom here, it would have 8 electrons, since, or 8 valence electrons, I apologize. If you look on the outermost shell here, there's just 4 groups of 2. This is a super common table given to us here, showing the Bohr-Rutherford model of common elements from the periodic table. You can see each of the valence electrons here in each of their respective outer shells. What I wanted y'all to realize is how the number of valence electrons are corresponding to each of the columns in here. And so what we end up coming across is atoms that form ionic bonds, as well as atoms that form different types of covalent bonds. Covalent bond is when typically exhibited by atoms who both want to gain electrons to complete their valence shell, as atoms completing their valence shell in that state. That is when they're so-called happiest. A covalently bonded compound would have 2 atoms sharing electrons, but not necessarily evenly. If they are evenly, that would be a non-polar covalent bond. That would mean that there's no dipoles, there's no uneven sharing, so to speak, between the 2 atoms. However, if there are, that would mean that you get partial charges within that compound. So let's look at, say, water, for example. Oxygen, it has a greater electron affinity than hydrogen does. This would be a hydrogen atom here. And so oxygen would have more time hogging the shared electrons from hydrogen than hydrogen has, just because it has a lower electron affinity. This would result in the oxygen atom having a partial charge of a negative atom, and then the hydrogen atom having a partial positive charge. Ionic bonds are essentially when, if we go to the periodic table here, it's when atoms from completely different elements, typically on opposite ends of the periodic table here, they interact with each other. So say lithium reacts with fluoride. It's instead of the sharing of electrons, it's the complete transfer of electrons. And this results in an imbalance within them, between the amount of protons that they have and the amount of electrons that they have, in order to have their valence shell filled. Positive ions are called cations, and negative ions, represented here by the chlorine ion, are anions. How my science teacher described this to me in high school was, they're called positive cations because cats are positive, and here they're called negative anions because no one likes ants. Another example here of ionic charges or ionic bonds being broken up are when they run into these partial charges, as I was discussing before, with polar covalent bonds. These polar covalent bonds, they interact with the charged ions in order to dissolve them within their own complex. A similar notion, or a similar phenomenon occurs in hydrogen bonding. It seems a little scary at first, but there's nothing really to be scared about. It's really just 2 atoms that aren't part of the same molecule, but still have partial charges, and they interact with each other. It's kind of similar to, say, if I was out walking my dog, and then my dog sees another person walking their dog, and she like nearly like rips my arm off to go say hi to that dog. She's not necessarily bonded to that dog, or she doesn't have a leash attached to that dog or anything like that. She just has an affinity to go to say hi to that dog. Same here with fluorine having a negative dipole, along with hydrogen having a positive dipole. It's like, oh yeah, I want to go say hi to you. Hey, what's up? I wanted to use those foundational topics to discuss the more macro structures that we were being tested on here. Specifically, there was the mineral lattice structure as well as the silica tetrahedron structure. The mineral lattice structure more so occurs when atoms, they orient themselves in like very specific points in order to form crystallized structures within their own right, based off of how each atom at what angle they bond. I'll give you an example here. Sodium chloride. This is a common formation within salts or ionic bonding. When you get the direct transfer of electrons over, typically atoms will arrange themselves in an alternating fashion, so that it creates like these really like pristine, cute structures such as so. Or you look at carbon-only structures that have been compressed under extreme amounts over time, such as a graphite structure or diamond structure. They compress themselves so that the carbon atom that's central here in each of these structures, they bond in such a way that it increases and optimizes the rigidity within the molecular structure. Silica tetrahedron is a commonly used one within the minerals classified as silicates. Here, this is kind of a goofy one that might throw a couple of you guys off, just because it's not necessarily a neutrally charged molecule or a neutrally charged monomer, as some people, as chemistry nerds would call it. That it would not be neutrally charged just because there's 4 oxygen atoms and a central silicon atom, which is weird, right? But I don't know, it's kind of just the way it is and the way it bonds. Essentially, according to the calculations here, oxygen has its own personal like net charge of -2, and when you have 4 oxygen atoms combined with a +4 net charge, let's call it, from a silicon atom, you end up with a net charge for the molecule of -4. The reason that people call it tetrahedron, or whatever you want to call it really, is that it just forms a triangle-based pyramid between the oxygen atoms and where they're placed in terms of their relation to their bonding angle in relation to the central silicon atom. It doesn't necessarily focus on the silicon atom, just in terms of naming the tetrahedron. Based off of these, a silicon tetrahedron unit, then they can form their own kind of polymers, like here. They can form single chains, double chains, or sheets. Typically when they're isolated, it's real handy because since they already have a -4 charge, they can use other cations just to sort of like space in between them and like fill gaps, and then create their own kind of little mineral structures. I just inserted a nice little table here for your guys' reference, as well as a couple other videos and some other links here to other educational websites if you've got